Hi guys. So I'm going to start this series on electricity and electronics by first of all going over some basic rudimentary fundamentals of electricity. Because before we start to put together our microcontrollers and circuit components and coding and transferring that code onto the microcontroller to do things, we need to understand exactly how electricity passes around a circuit and how energy is transferred from one end of the circuit to the other. And it's also beneficial for those of you taking GCSE physics or A-level physics because I will give a thorough revision of electricity. So the first thing that we need to go over, the first definition that we need to go over is the definition of voltage. And simply being, the voltage is equal to the energy transferred over a certain population of charge. Okay. So I have a bunch of energy and I have some charges waiting to receive that energy. What I'm doing as the battery or as the sort of entity in the circuit, I am taking that energy and I'm dividing it amongst the amount of charges that I see. So as I've written here, voltage is the energy transferred to a population of charge. It is also the work done on a charge carrier due to an external electric field. So inside a battery, especially an electrolyte battery, you have chemical reactions happening and you have a potential set up. And in that potential, in that variation of potential, work is done on any charge. So energy is transferred from the electric field to charges that may be passing through, and that is how electrons get their energy and exit the battery into the rest of the circuit. So voltage V, the symbol V, is measured in volts. The energy E is measured in joules, J, and charge Q is measured in coulombs. So the unit of voltage is not only volts, but the base unit is actually joules per coulomb. Okay, energy per unit charge. The next important definition that we need to understand is the definition of current. Simply being, current is the charge flowing divided by the time spent measuring. And it doesn't even have to be charge. It could be for water or it could be for people. If I was on the street and I was looking at a certain point on the street, the charges would instead be people. So it would be people divided by the total amount of time that I spent measuring them. So current, with respect to electricity, current is the total amount of charge carriers passing a point in a certain amount of time. So if I measured 30 charges passing over a space of 60 seconds, my current would be 0.5. So I would have a charge every half second passing. Current I is measured in amps. So this is the common standard unit. Charge Q, as we know, is measured in coulombs. Time T is measured in seconds. So the fundamental unit of current is actually coulombs per second. How many charges or what total amount of charge is passing a certain point in the circuit per second. Next up, the next important definition is resistance. So here I have my artist's impression of a block of metal. The big red circles are metal ions, and these are positively charged. Okay, so every single one of these metal ions is positively charged. I'm not going to do all of them, but just so you know, they're positively charged metal ions and they are arranged in a fixed metallic lattice. Okay, and in between them, the blue dots are delocalized electrons. So delocalized electrons are electrons that are not bound to any of the atoms. They are free to flow. And I have the green arrows to illustrate the pathways which they may take. Now, what will happen is that during the course of current flowing through a metal conductor, there will inevitably be collisions. So collisions between the delocalized electrons and the metal ions. Now, the electrons already have voltage. They already have a certain amount of energy that they're carrying. So each electron basically carries a portion of that energy. In a collision, that energy is transferred to the metal ions. And that electron is basically, let's just say it's lost. Okay, it's lost. And because energy is transferred from the electron to the metal ion, things slow down. So that's how you get the impedance from. That's how you get the obstruction from. Okay. So resistance is the impedance or obstruction to the flow of charge. If I put something in your way as you're running and you bump into it, you lose energy. Because you lose energy, you either stop or slow down. So therefore you are impeded or obstructed by that object. Resistance therefore manifests as collisions between electrons and the material which they travel through. Now the equation for resistance is resistance equals the resistivity multiplied by the length over the cross-sectional area. Now the length of the wire or conductor and the cross-sectional area of the conductor are pretty self-explanatory, but the resistivity is an inherent property of said conductor. The resistivity can be related to how dense the metallic lattice is. It could be related to the electronegativity of the metal ions that make up the metallic lattice. So say if it's maybe an alkali metal, an alkali earth metal or group 1 metal. If I recall correctly, those metals are a bit more electronegative than the transition metals. I could be wrong. Actually, they don't make good. Yeah, they don't make good conductors. So, yeah. Anyway, it's an inherent property that basically decides how good this material is at resisting anyway. Okay, and it could also be related to how many electrons said metal ion has in its outer shell, and that will determine how likely other electrons are going to be bound to it. Every single material has a specific value of resistivity attached to it. Okay, moving on. Ohm's law. Now, this equation is very, very important for circuit analysis. Ohm's law is the voltage equals the current multiplied by the resistance. If you were to be asked, oh, what's the definition of Ohm's law? What does Ohm's law mean? It simply means that the voltage is proportional to the current given that the resistance remains constant. So Ohm's law is actually more applicable to well-behaved circuits. So here I have 3 examples of Ohm's law behavior. In the first example, I have a perfect resistor. This is basically a resistor that does not change its properties irrespective of how hot it's getting or how much current is flowing or how much energy I'm putting into it. And as you can see, the voltage is proportional to the current every step of the way. On the flip side, I have a filament lamp. So we know how filament lamps work. They produce light by having a current pass through a filament. That filament has a high resistance, it gets hot and it starts to glow. In this region here, centered about the origin, the filament is well behaved because the voltage is proportional with the current. However, at even higher currents, at even higher voltages, the current gets higher, but because they have so much more energy, when they eventually collide into metal ions, the energy transferred is greater, so the metal ions will be given more energy on collisions. Now, because the metal ions are now energetic, they will be vibrating and they will be blocking off the pathways for the current to flow. So you will have a hot conductor that's just vibrating, that has its metal ions vibrating all over the place, and it's extremely good at obstructing the flow of charge. So eventually you're going to get to a point where you start to have a plateau because it was your voltage is going straight into the metal ions due to the collisions happening. So you're not actually transferring that energy to the electrons to make them flow faster, thereby increasing the current. they're going to the electron straight to the metal ions. That's why you get the plateau. And here we have a diode, and this is basically showing that diodes behave in a way where current can only travel in one direction. That's why at below a certain voltage, there's no current flowing, but after a certain voltage, a current flows. So Ohm's law is the primary expression to use for circuit analysis. Here I have a basic series circuit with two resistors of arbitrary resistances. And I can use Ohm's law to tell me about the entire circuit. So Ohm's law is V equals IR. So here I've used V equals IR and I've substituted V for the total voltage into the current. I've substituted I as the total current flowing through the circuit. And I've substituted R as the total resistance due to the addition of both resistances. I can also use Ohm's law to look at an individual component. So if I was to look at just this resistor and put a voltmeter there in parallel, I can see the voltage lost on R1. Because it's a series circuit, the current stays the same. And the resistance of R1 is basically the resistance of R1. So I can use V equals IR to tell me about what current is flowing through R and the voltage dropped across it. So it's a very, very, very helpful equation to use. Kirchhoff's laws. Kirchhoff's laws are basically conservation laws that tell you about the behavior of a circuit. The first law is the current law, and that says that the current flowing into a junction. So if you had a parallel circuit, there's obviously a junction. The current flowing into a junction must be equal to the total current flowing out of it. Here I have a current I4 splitting off into three smaller currents, I1, I2, and I3. It so happens that I1, I2, and I3 added together equals I4. And this is just a statement of charge conservation. The energy conservation law is the second law. And that says that the sum of all voltages around the closed circuit must be equal to 0. So if I had a known voltage on the battery and I had voltmeters on two resistors in series, I would be measuring that both voltages added together that I measure on the resistances should be equal to the resistance should be equal to the voltage coming out of the battery. And on the right side, I've just got the math showing. Okay. Internal resistance. Internal resistance basically states that no battery is perfect. Every battery or cell has an inherently small resistance. So basically, electrons lose energy just by attempting to leave the battery. So the voltage rating on the battery is not exactly the same as that seen by the rest of the circuit on the terminals. The terminal here that I've denoted in orange. So here's another simplified series circuit. I have a battery and I have its internal resistance. The battery has a voltage V0, but because of the internal resistance, some of it is lost. So I've got I times R, so that's a voltage, I times R, Ohm's law. And some of the voltage is lost. So what the rest of the circuit sees is actually the terminal voltage. And the terminal voltage is the battery voltage subtracted by the voltage lost on the battery's internal resistance. Last but not least, series and parallel circuits. In series, you basically have things in a line, okay? Just one after the other. And in a series circuit, voltage is dropped across each resistor, so you lose voltage as you go through the circuit. However, the current stays constant. The same current at this point, here is the same current at that point, is the same current at that point. On the flip side, you have parallel circuits. Now the voltage stays constant. Because the voltage is how much energy does each electron have. It doesn't matter if R1 is 1,000,000 and R2 is only 5. So long as one electron goes in there, it will still have a certain amount of voltage. So let's say that I have 5 volts. Every electron has 5 volts. 1,000,000 electrons with 5 volts each can go in there. One electron with 5 volts can go in there. That's why I state here that voltage stays constant. However, the current varies because the current needs to split at the junction. Remember Kirchhoff's First law, the current needs to split at the junction. And this expression here basically just tells us if I have some resistors in series, what is their total resistance? Because we would be able to treat it as one combined resistor. Okay, so in the next lesson, we will be looking at some basic circuit components. And actually, we will draw a couple of circuits and see how they work on an actual real life circuit. So an application of electricity.